In this video, we will examine how atoms interact with each other through intramolecular interactions such as covalent and ionic bonds, and how molecules can interact with each other through intermolecular forces such as hydrogen bonds. Intramolecular forces are interactions between atoms which hold atoms together within a molecule. These are the interactions which allow molecules and compounds to form. The formation of intermolecular forces is based on the number of electrons in the outer shell of an atom, also called the valence electrons. The three types of intermolecular forces we will focus on will be nonpolar covalent bonds, polar covalent bonds, and ionic bonds. We will start by examining covalent bonds. All covalent bonds, both nonpolar and polar, are formed when two atoms share their valence electrons so that they can all have a full outer shell. The figure shows two hydrogen atoms forming a covalent bond with one another to make hydrogen gas, also written as H2, with the subscript indicating how many atoms of the element are part of the molecule. H2 would represent the chemical formula, a way of showing what atoms and how many of them make up a molecule. If you looked up hydrogen on the periodic table, you would find that it has an atomic number of 1. This means that it has one proton in its nucleus surrounded by one electron in its outer shell. On a side note, hydrogen is different than all other atoms in that the standard hydrogen atom does not contain any neutrons in its nucleus. Keeping in mind that the first electron shell can hold 2 electrons, a hydrogen atom will need one more to fill its outer shell. A covalent bond is formed when 2 nuclei of the atoms move close enough together so that they can share their 2 electrons with both nuclei. So as the second hydrogen atom gets close enough to the first, they are both able to share their single electrons, which will then travel around both nuclei, sharing those electrons, filling the outer shell, and holding those 2 atoms together with a covalent bond. This can also be written using the structural formula, where a pair of shared electrons is represented by a single line, such as this, hydrogen bonded to hydrogen, or by a Lewis structure where the valence electrons are written as dots, such as hydrogen bound to hydrogen. When atoms share their electrons to form covalent bonds, the orbital location of shared electrons will determine the shape of the molecule that is formed. This is very important in biology because molecules are 3-dimensional structures, and the shape of each molecule provides it with the physical and chemical properties required for its function. You will hear many times in this course that shape equals function. As an example, let's look at a water molecule, H2O. Remember, H2O would be the chemical formula, stating a water molecule is composed of 2 hydrogen atoms and 1 oxygen atom. If we look at the Bohr diagrams for each atom individually, we can see how the covalent bonds form. Each hydrogen atom again has 1 proton in the nucleus, surrounded by 1 electron in the outer shell, needing 1 more electron to complete the outer shell. Oxygen has an atomic number of 8, meaning it has 8 protons in its nucleus and 8 neutrons, surrounded by 8 electrons. 2 of those electrons will be found in the first shell, leaving 6 to be added to the second shell. Filling the second shell, it is important to remember that each orbital gets 1 electron before any orbital has a second electron added to it. Thus, 4 electrons first fill, and then we go back to the first orbital to fill in the remaining 2, giving us a total of 8 electrons around the nucleus. If one hydrogen atom shares its lone electron with the orbital of oxygen, and a second hydrogen atom shares its electron with the other empty orbital, we will get a molecule of water. This sharing of electrons is depicted in the figure here. It can also be written as a Lewis structure diagram by drawing in only the valence electrons. Oxygen with individual pairs on the outside, and then shared valence electrons with hydrogen. When two atoms share electrons, they do not always share them equally. An unequal sharing of electrons, where electrons will spend more time circling the nucleus of one atom instead of the other, will generate a polar covalent bond, while equal sharing generates a nonpolar covalent bond. The key property of atoms that will determine their electron sharing is electronegativity. Electronegativity is based on two factors: the number of protons in a nucleus and the distance the valence electrons are from the nucleus. Remember that protons have a positive charge while electrons have a negative charge, and opposite charges attract. This means the more protons in an atom's nucleus, and the closer to the nucleus the electrons are, the more protons will be pulling on those shared electrons. Using oxygen and hydrogen as an example, we see that oxygen has 8 protons in its nucleus, while hydrogen has only 1 proton. The 8 positive charges will have a much greater pull on a negative electron than 1 positive charge. Thus, oxygen is more electronegative than hydrogen. When an atom with high electronegativity, such as oxygen, forms a covalent bond with an atom with low electronegativity, such as hydrogen, a polar covalent bond is formed, because the shared electrons spend more time circulating the nucleus of the high electronegativity atom than they do the low electronegativity atom. Because electrons are negative, and they are spending more time around the nucleus of the high electronegativity atom, they cause an increase in negative charge that is not canceled out by the positive charges in the nucleus. This causes a partial negative charge on that atom. The hydrogen atom is the opposite, gaining a partial positive charge. Partial charges are depicted with the lowercase Greek letter delta. A molecule with partial charges formed by polar covalent bonds is called a polar molecule. Water is an excellent example of a polar molecule. A nonpolar covalent bond is formed when the atoms sharing electrons have similar electronegativities and form neutral molecules with no partial charges. Hydrogen-hydrogen and carbon-hydrogen bonds are nonpolar covalent bonds, as seen in the two molecules shown. An ionic bond is an attraction between two ions. The definition of an ion is a charged atom, and they are formed when an atom loses or gains electrons in order to fill its outer shell. An example of a compound held together with an ionic bond is sodium chloride. Sodium atoms have an atomic mass of 11. This means they have 11 protons and 11 neutrons surrounded by 11 electrons. 2 in the first shell, 8 in the second shell, leaving 1 final electron in the third electron shell. We have not talked about the third electron shell yet, but it can hold a total of 8 electrons, similar to the second. This means in order to be most stable and have a full outer shell, sodium would either have to lose 1 electron, losing its third shell completely and leaving it with a full second shell, or gain 7 electrons. It is much easier to lose 1 than gain 7. Chlorine has an atomic number of 17, so it has 17 protons, 17 neutrons, surrounded by 17 electrons. 2 in the first shell, 8 in the second shell, and the remaining 7 in the third shell. In order to fill both outer shells, sodium completely loses its single valence electron, and the electron is taken by the chlorine atom. This loss and gain of electrons generates a sodium ion and a chlorine ion, charged versions of the atoms. Sodium has lost an electron. It now contains 11 protons, or positive charges, and 10 electrons, or negative charges. So what would the overall charge of the ion be? It would be a charge of +1. Chlorine, on the other hand, now has 17 positive protons and 18 negative electrons, so it would have a negative charge. What happens when you put opposite charges together? They attract. It is that attraction between the two ions which forms the ionic bond and holds the ions together to make sodium chloride. Ionic bonds are weaker than covalent bonds due to the nature of their formation. Water is the medium of life. This is why, as NASA explores space, you always hear excitement about planets and moons which may contain or may have previously contained water. We just mentioned that the partial charges of a water molecule allow it to dissolve many things, making it a good solvent. Those partial charges make water a polar molecule and is able to interact with other polar molecules. Molecules which interact with water are called hydrophilic or water-loving. Those which are nonpolar do not interact with water and are called hydrophobic or water-fearing. Oil is a good example of a hydrophobic molecule. Water has many unusual properties which are key for life to exist on this planet. Those properties form because polar water molecules are able to form hydrogen bonds with one another. A hydrogen bond is an intermolecular force that can occur between different polar molecules. It occurs when a partially charged positive hydrogen atom interacts with a partially charged negative atom on another molecule. The dotted lines in the picture represent the hydrogen bonds holding water molecules together. These bonds are weaker than covalent or ionic bonds, but play a major role in water chemistry as well as in stabilizing macromolecules of the cell, such as DNA and proteins. Hydrogen bonds give water many unusual properties, including allowing ice to float, providing adhesion and cohesion characteristics, and the ability to resist temperature change. This ability is obvious when cooking. The water in the pan always takes longer to heat than the metal of the pan itself, due to the hydrogen bonds holding the water molecules together. A video is provided in Canvas if you would like more detail on the unusual properties of water.